Hello, everybody, and welcome to lecture for Geo 572 Advanced Hydrogeology. Today we're going to be talking about numerical methods for solving partial differential equations, and we're going to get introduced to the first and simplest numerical method, and that is finite differences. So in our last lecture, we talked about developing analytical solutions that solve the boundary value problem and develop or provide a solution to a partial differential equation given a domain of interest, given a governing equation, boundary conditions and initial conditions, and given the parameters that control given the parameters of interest in our partial differential equation. So we developed an analytical solution for a very specific case, and it turns out that in the real world, those cases in which we can find an analytical solution are very rare. And it's difficult to come up with them. And so especially in the world of earth sciences, we tend to move away. We use analytical solutions when we can, but for more complicated situations, we're going to use numerical simulation, or in the world of groundwater models. And all these groundwater models are doing is solving the boundary value problem, so estimating the solution to a partial differential equation subject to boundary conditions, a domain of interest, initial conditions, and the parameters, subsurface parameters that control groundwater flow. So today what we're going to do is take a look at the most fundamental method of numerical methods, and that is finite differences. Okay, so we developed an analytical solution for the heat flow equation, one-dimensional heat flow equation. And today I'm going to look at developing a finite difference for the groundwater flow equation, which has the same shape and is the same kind of equation as the heat flow equation. So let's go back and recall our partial differential equation for one-dimensional, transient, homogeneous, and isotropic groundwater flow. And that is dH dt is equal to K d squared H dx squared. All right, so specific storage times the change in head with time is equal to the hydraulic conductivity times the curvature of the head in the x direction. All right, and I'm going to do a little algebra trick here. I'm going to rewrite this as dH dt is equal to alpha sub h d squared h dx squared, where alpha h is equal to k over ss. And this, the hydraulic conductivity over the storage, is called the hydraulic diffusivity. All right. Okay, so this is our governing equation here that we're interested in solving. And you know, a solution, if we recall, a solution to this equation would give us some function. Let's call this 1. So a solution to 1 would give us some function that gives us the head, all right, as a function of x and t, all right? So this is a continuous function in the x dimension and in time, and it gives us the head. So as an example, we might have our solution might look something like this. Here's x, here's h, and we might have a curve, continuous curve that looks something like this at t equals t sub I, and then we might have another curve here at t equals t sub I plus 1. All right, so this is our initial head, or this is what our head looks like at time t equals to t sub I. This is what our head along the x direction looks like at some time later, t sub I plus 1. All right, and a solution would give us these curves and how they evolve through time. All right, so that's what we're looking for when we derive a solution here. The problem is that we don't often have a solution that we can derive, an analytical solution. So what we're going to do is we're going to look at separating or dividing these curves and estimating them at a series of points. All right, and this is the whole thing with finite difference. We have this series of points that we're going to estimate the solution, all right, to our differential equation at. And there's a couple critical things. So analytical solution is a continuous function. That means we could find it for any value of x and t. We have this continuous curve. In a numerical solution, we're going to discretize, all right? So dividing this up is called discretization. So we're going to discretize our curve. All right, and we're going to divide it up and we're going to estimate this curve at a bunch of different specific points. So we're going to estimate curve. We're going to estimate h of x and t at specific points. Let me clean this up here. All right, estimate. So at each one of these points, we're going to estimate the curve. All right, and we're going to do this in finite differences by dividing this curve up into even increments. All right, so finite difference, and these are separated. Let's zoom in. Let's for now just zoom in on a single one of these curves. All right, so I'm gonna zoom in here and just consider one of these curves. All right, so we've got this curve here. All right, And again, this is the X direction and this is head. All right, so we've got this curve and we're going to look at a bunch of points. All right, so we got this series of points. We discretize our curve. And I'm going to label these. So this point right here is point I. All right, this curve, this point here is I minus 1. This point here is, can you guess it? I plus 1. All right, and they kind of go on. And I'm also gonna think about two other points here. This one and this one, which are exactly halfway between I minus 1 and I. And this one is I minus 1/2. All right, and this one we're going to label as I plus 1/2. All right, so these are the indices, and all of these are separated. These are separated by some distance. Come down here, they're separated by a distance, delta x. All right, and each one of these points is separated by this distance, delta x, and in fact, so are these two. All right, if they're exactly halfway in between the other 2 points, these 2 points are separated by delta x too. All right. Okay, so the point here is that I'm going to separate this curve up into points that are all delta x apart. All right. And I'm going to look at this point I, and I'm going to have you remember way back to calculus 1, all right? And you thought it would never be useful when you did this in class, because I certainly thought that. And we're going to remember this, a Taylor series expansion. All right. And what a Taylor series expansion said way back from calculus 1 is that if I wanted to estimate the value of head at this point, x plus delta x. So let's say I'm interested in h of x plus delta x. Right, and if I look at that, that's really this point I plus 1 here. That's 1 delta x away from my point I. This is equal to the value of the head at the point x, all right, plus the derivative at the point x, f prime of x, all right, times delta x, all right? So you can think about that as we're going to say it's this plus the slope times delta x, right? Plus the curvature, all right, times delta x squared over 2 factorial. And this keeps repeating. Plus f triple prime of x times delta x cubed times 3 factorial. And this just keeps going on and on and on. All right. Okay, so I can rearrange this Taylor series expansion, and I could say that I'm going to rearrange it for f prime of x. And I'm going to say, well, f prime of x. Actually, let me, I'm sorry. This is a mistake on my part. this is h prime. That's what we labeled our function, h prime of x, all right, at x is equal to h of x plus delta x minus h at x, all right, over delta x plus all this other stuff, order second and above. That's all this other stuff here. All right, and what the fundamental assumption here in finite difference is that as delta x gets really small, delta x squared gets even smaller, delta x cubed gets even smaller, and so this guy, if delta x is small, this goes to 0. All right, it gets small. This error here, or this stuff here, gets small. All right, so that gives us the first finite difference equation, and that is that my derivative can be approximated by this situation here. So now I'm going to go back up here, and I'm just going to I don't need to go back up, actually. I think we can do this in our minds. I'm going to say our first fundamental finite difference equation is that I'm going to, instead of h prime of x, I'm going to write this out. So I'm going to say, for example, dh dx is equal to the head at x plus delta x, all right, minus h of x over delta x. And I'm going to put a squiggle here. It's approximately equal to this. And this is our first finite difference equation. All right, and I'm gonna do something next. I'm gonna say, well, can't we call h of x plus delta x? Couldn't we also say that in our I notation, this is h x of I plus 1, right? That's x plus delta x minus h x of I over delta x. Okay, so this is the first derivative in finite difference. All right. These two equations, they're the same exact equation. Here, I've just made this in terms of I. So this is x plus delta x is the same as x, I plus 1. H of x is the same as h x I, and delta x is the distance between them. Okay. First important equation. Let's give this some excitement. And let's call this guy star. All right. Okay. I'm going to now define the central difference operator dx. All right, and all dx is this. It says, instead of doing this at using the value delta x above and the point, I'm going to look at that half spacing in between. So this would be h x I plus 1/2. All right, this is the half step ahead minus h x I minus 1/2. All right, over delta x. All right, and all I'm doing is this is the derivative, but using the points half a step behind and half a step forward. It's exactly equivalent. It's just moving. It's exactly equivalent to star. It's just moving the template by 1/2 spacing. All right. And I'm going to use that here to derive the equation for the second derivative. All right. So what I'm interested now is the second derivative. All right. D squared h dx squared. That's what we're after. All right. And this is basically equal to, or this is approximated by, the central difference. Sorry, it's not z, it's x. All right, so this is like the derivative or the finite difference of the finite difference of h. All right, and this is equal to the central difference operator squared of h. All right, so let's think about, let's expand this. All right, and come down here and say, well, this looks like d dx, or the central difference operator, and then I'm going to put in here this. So this is h x I plus 1/2 minus h x I minus 1/2 over delta x. All right. And then I'm going to just do some algebra here. So first I'm going to pull out this delta x. All right, all I've done is pull x out and distribute my operator. And if I look at this operator, all right, So let's 1 over delta x, all right, times. Now let's look at this. This is, if I move my template, I'm going to end up, so the same, so I'm going to expand this around h. I'm going to move 1/2 step forward, all right, from hxi plus 1/2. So I'm going to end up here. This is going to look like h of x plus, oh, sorry. Let's stay in I here. I plus 1, right? That's 1/2 step up from xi plus 1/2, all right? Minus 1/2 step down from I plus 1/2, hx sub I, all right, over delta x. And all this is here, this is this term going here, all right? And I can do the same thing here. This becomes h x, all right? I'm going to move up 1/2, so I go to I, and then I'm going to move down 1/2. Which is gonna, yeah, that's gonna move me to h x I minus 1, all right, over delta x. Bada boom. And all this is multiplied then by delta x. Okay, so now I'm just gonna rearrange here, and I'm gonna get my second derivative. And that looks like this. My second derivative operator, d squared h dx squared, is basically approximately equal to, I'm going to pull delta or multiply by delta x in here and then combine like terms, and we're going to end up with h of x I plus 1 minus 2 h x sub I plus h x I minus 1 over delta x squared. All right, so this is my second derivative operator in finite differences, and we'll call this guy double star. Okay, so now I'm going to combine star and double star and rewrite our, so recall that we have our governing equation looks like this: dh dt is equal to alpha d squared h dx squared. All right, so we've got a single or first derivative here, and we've got a second derivative here. And so I can use star here, and I can use double star here. All right. And I can rewrite things. So this now, our discretization is in time. All right, so I'm gonna add a little twist here. I here is always going to be our spatial discretization, but J is our time discretization. It's the exact same. We're just dividing time up. We could think of, let's just do it here. This is time, and this is H, all right? And we've got our head varying with time. So this we're going to call, J. This is J plus 1. This is J minus 1. We've just discretized by now delta t, all right? So I can use my same operators, but I'm gonna have two notations. This is J plus 1 minus H, same spatial place, J, all right, over delta t, all right? So this becomes my right-hand side or left-hand side, alpha. And now I'm going to use double star, and I'm going to stay at the same time step. So H, J, I plus 1 minus 2, H, J, I minus, plus H, I minus 1, J over delta x squared. Okay, this equation right here is the fundamentals of the finite this is the finite discretized form of our governing equation. It's got the left-hand side, it's got the right-hand side, and we can now use this to solve for some important things. So let's, for example, let's think about what the head is at some spot at the next time. All right, so let's solve this equation for this guy right here. This is the head at some spot at the next time step. All right. So H sub I, J plus 1. So the head at our ith spot at the next time step. All right. And I'm going to do some algebra and rearrange. You can do this in your own time. H, I, J plus R. I'm going to define R in a second. H, I minus 1, and J. Plus R, H, I plus 1, J. And here R, well, you can guess it's just a combination of moving delta t over here and delta x out here. So R is equal to delta t times alpha over delta x squared. All right, it's just combining all these into one term, and then all I do is solve. All right, multiply through, algebra solve. All right, so what this does, this says, oh, hey, you can calculate the value of the head at the next time spot from all the heads around it at the last time spot. All right. So if I have initial conditions, I can just go ahead and calculate the head at the next point by looking at the head values around all my other, around in the surrounding area. So this is, we're going to call this 2. This is the explicit method. All right, and it basically says I can find the value of the head in the future using the heads I know right now. All right, so this predicts future, predict future. From current head. And you could imagine that it's pretty easy for me to write some kind of a script or something to say, all right, look at the values of the head at some point on either side, run this equation, output a value of head at the next time spot. I do that for every place, every X location. All right. And then I have a new set of heads at the next time, and then I march forward in time. Right? So that's called an explicit method. The problem with the explicit method, it will, so the explicit finite difference will converge when R is less than 1/2. All right. That means delta T is equal to delta X squared over 2 alpha. All right. So essentially what this is saying is I have to take time steps. I will only converge. This will only work when my time steps and my space steps are small enough. All right, when R is less than 1/2. Okay, so there's another way we can look at this, and that is by looking into the future to get the past. So let's talk about the implicit method. And in the implicit method, what is happening? So in the implicit method, we use the future to get present. So cool. Only in math can we look forward in the future to get our current conditions. All right, so I'm going to rearrange our equation, and that is 1 plus 2r t I and gosh, switching notations on you guys, sorry. H I j plus 1 minus r H I minus 1, j plus 1, minus r h I plus 1, j plus 1 is equal to h I j. All right, so I'm looking at all the values of head in the future to get the value of the head at my current location. So all these j's have been advanced to j's plus 1, all right, and the spatial discretization stays the same. All right, and I can think about this as a set of matrix equations, all right, and they look like something like this. I got this matrix and 1, 0, dot, 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 dot. And these have certain lengths. And it's going to be minus r 1 plus 2r r, and this is being multiplied by, let's say this is h of 0, j plus 1. All right, this is my boundary. So x equal to 0, dot, dot, dot. And here I have h, j plus 1, I minus 1, h, I, j plus 1, h, I plus 1, j plus 1, dot, dot, dot. So this is a vector of the heads. This is a matrix. And if you haven't done this before, or if you need a refresher, when I multiply a matrix, I take this row and I multiply every element of this row down this matrix. And that essentially is going to give me the value of my head. So this would be h naught, my boundary at my 0, 1 times h naught, and then this is zeros all the way away. So that gives me h naught. And this one, dot, 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 where I multiply these guys in against these, gives me h, I, j. All right. So I get I can write this matrix. Let's call this matrix A. Let's call this vector, this is H. So bar over it means a vector, J plus 1. And this is H, my vector of values at J. All right. So A, the matrix, times my vector of heads at J plus 1 is equal to the vector of heads at time J. All right. Now, we can't really know the future without knowing the past. So what we're going to do is Hj is equal to A inverse, all right, which is essentially the matrix algebra version of dividing times H J plus 1. All right. Sorry, H. Mess this one up. H j plus 1 is equal to A inverse times hj. All right, and this is called the implicit method. And the trick with the implicit method is this, finding this A inverse, all right? But the good thing about the implicit method is it's convergent for all time steps. Okay, so what we're going to do in class is we're going to use, we'll call this 3. We're going to use 2 and 3 to look at finite difference solutions of the groundwater flow equation. All right, and for 2, it's pretty easy. We can use Excel, and for 3, we're going to use Python and code up this solving for this vector from the previous vectors. Okay, we'll see you in class, and we'll do some finite differences. Talk to you later.